Hello, good day. Welcome to the second part of our discussion for integrated circuits. As you might remember from last time, we were able to discuss some concepts involving integrated circuits, levels of transitions, types of integrated circuits, and main applications of integrated circuits. So, for the second part of our discussion, we will be focusing on two main topics. The first one would be one of the common types of circuits integrated as an IC, which is a multivibrator circuit. More specifically, the use of a 555 timer. The last part of today's discussion would also be discussing one of the main problems in electronics communication, which is noise. Anyway, let's get started. So we were able to finish the types of transistor integrations up to the largest, which is terascale integration. So for today, let's now go into the discussion of a multivibrator circuit. So what is a multivibrator circuit? So a multivibrator circuit is simply put is a circuit that produces an output between high and low state. Now, the types of multivibrator circuits actually depends on how many times the circuit output changes from high to low, as you would see later. One of the main importance of the multivibrator circuits is that it is used as a clock signal for synchronization. And believe me, when we go into further discussions on electronics and electronics communication, the term clock signal would actually come up a lot. And when you hear the word clock signal, you may think of, or you should think of, the multivibrator circuit. Now, before we go to the types of multivibrator circuits, let's look into a possible output of a multivibrator circuit, which is usually a square wave circuit. So the square wave actually has several highs and lows. Okay? It's clock width, rising and falling edge, and clock period. So let's go ahead and define each and every term or parts of a clock signal waveform. So first, we have the active high and active low. Now, when we talk about digital circuits and digital signals, we usually think of binary signals having only ones and zeros, highs and low, which is commonly true, or which is true commonly. But when we talk of digital circuits, in a more technical sense, digital signals have countable number of possible states. So it's not really just 3 or 2. So if it's just countable, the number of states, then it is considered a digital signal. But in most cases, it's actually only 2, high and low. But what is its main difference between active high and active low? One of the things that you would be discussing when you talk more of the different integrated circuits or ICs, both for digital signals, is what we call the active high and active low state. When we talk about active high, it means that that specific pin or function of the IC activates when its input is high or it's in the rising edge, meaning when there's a transition from a low state towards the high state. Now, when we talk about active low, it means that the function of that specific pin in an IC activates when it encounters an input of a falling edge, meaning a state where it transitions from a high state into a low state. So when we talk about the most common timing circuit, which is the 555 timer, we'll actually look into an active low state in several of their pins, if I'm not mistaken. Next, we have what we call the duty cycle. The duty cycle is termed as the ratio between the clock width and the clock period. So if the clock period or the clock width, meaning the duration of how long the clock is in the high state, is half of the overall clock width being the duration of one cycle, then that would have a 50% duty cycle. If the clock width is on or at the high state 3/4 of the time compared to the clock period, let's say 7.5 seconds, it's in the high state, 2.5 seconds, it's in the low state, so 3/4, that would mean that the clock signal waveform has a duty cycle of 75%. In the illustration here, we might be able to see that around 50% of the time it's in the high state, 50% of the time it's in the low state. So 50% is the clock width, the clock period is the duration of both high and low, which is one clock cycle. So that would give us a duty cycle of 50%. Now, if for some instance an output of the signal never goes down into a low state or it is in a constant high state, then that means the duty cycle is 100%. Now the opposite is also true. If the output of the waveform is always in the low state, never going into high state, then that means the duty cycle is 0%. We talked about the clock width and the clock period a while ago. The clock width, again, is the duration that the signal or the clock signal is turned into a high state or logic 1. The clock period would be the total duration of both the combination of the low state and the high state. Another way to define a clock period is the time between two successive rising edges or two successive falling edges. For example, we have the first rising edge here, and the next rising edge is somewhere here. So the distance or the duration in between the first rising edge and the second rising edge rather is the clock period. We could also measure the clock period by looking at the duration of two consecutive falling edges. So this is the first falling edge, high to low, and this is the second falling edge, second high to low. So the duration of this would also be the clock period. In a proper clock signal waveform, that should be constant and consistent. Next, we have the clock frequency. The clock frequency, as with signal frequency, would be the reciprocal of the clock period. That means we could actually determine clock frequency if we divide 1 with the clock period. With that being said, let's now go to the types of clock pulse generation circuits or types of multivibrator circuits. The 555 timer, which you would be discussing later, could actually be configured to do or to become these three types of clock pulse generation circuit. So it could be programmed into an astable circuit or a stable multivibrator, a one-shot or monostable multivibrator, and a bistable multivibrator. So what's the difference between the three? When we talk about the astable circuit, it means that there is no stable state. It means that the states continuously change in a fixed duration. So it continuously changes from high to low. Then after duration, it would change from low to high. And then high to low to high, continuously forming a square wave output or a train of square wave pulses. When we talk about monostable clock pulse generation circuit, also called a one-shot multivibrator, it has a single stable state. Now, its stable state depends on the design of the clock pulse generation circuit. So you could have a stable circuit of low or a stable circuit of high. So if you have a one-shot multivibrator and you have a stable state of low, once you trigger the clock pulse, it would go into high. But after a specific period, it would go back into its stable state of low without needing an external trigger. Now, the opposite is also true. If its stable state is high, that means if I put in an external trigger, or an external input, it would shift to low, which is its unstable state. Then after a specific period, it would go back into its stable state, which is high. Again, as mentioned, its stable state depends on the design, the duration of the width of its unstable state, meaning how long before it goes back into its stable state, also depends on the design of the circuit. Now, what is its difference with the bistable state? As the name suggests, the bistable state has two stable states. So it could have a stable low and stable high. So what is its main difference with monostable? In monostable, you don't need an external input for it to return to its stable state. You need an external input to shift it to its unstable state, but it would automatically revert back or revert to its stable state after a specified duration according to the design. But with the bistable state, you use an external trigger to shift it to another state, so from low to high or high to low, and it would stay there unless you put in another trigger. Okay, so let's say we are in low state right now. So once I put in a trigger, it would shift to high. It would stay there unless I put in another trigger. So when I put in another input trigger, it would now shift to its low state. So it means that I am fully controlling the duration of its high state and low state through the use of a trigger. Unlike with the monostable, it automatically reverts back into its stable state. The most common IC used to create a multivibrator circuit is the 555 timer. So it's a very common, popular, and useful precision timing device. So for most general purpose timing needs, the 555 timer would suffice. So it could be used as a simple timer to turn signals on and off, or you could use it as a relaxation oscillator to be able to determine its to turn its unit on and off, just like a train of square wave circuits, or like a multivibrator, a stable circuit. So let's look at some of the pinouts for a 555 timer. I'll try to explain the design inside the 555 timer, but we'll have a separate discussion with the function of how the 555 timer operates. And then the third part of our discussion next week or this weekend would be, or the next video would be focusing on some design calculations or computations in order to control the amount of timer circuit or the width of the pulse duration. So a 555 timer has 8 inputs or 8 pins. So pin 1 is the ground. So the pin 1 connects the timer to a negative supply rail. So normally in every IC, there would always be a positive or a negative supply. So it's usually in pins 1 and the last pin. In this case, that would be the pin 8. So pin 1 is usually the ground, and the last pin, in this case pin 8, is usually the positive supply. So pin 1 ground, we usually connect it to the negative supply or negative part of the supply. Pin 2 is the trigger. So we use pin 2 as a way to connect or to activate our multivibrator circuit. So when we have our design and discussion of the operation of a 555 timer, we would be able to show you the importance of the trigger, especially when you go into the course of digital logic circuit design. The output is gathered from pin 3. Okay? So if we're going to create an astable, one-shot or a bistable multivibrator circuit, then we get its output from pin number 3. Now, usually in a 555 timer, it can drive or sync up to a 200 milliampere current up to a voltage of around 1.5 volts, or at least 1.5 volts. So that current or power is actually enough to power LEDs, small motors, and low power applications. Pin 4 is used to reset the internal configurations inside the 555 timer, specifically the flip-flop. We'll talk about flip-flops when you get into the course of digital logic circuit design. So, but you just have to understand that when you press reset, the contents of the flip-flop is set into its original configuration. By the way, before we go to pins 5, 6, 7, 8, let's look at the internal circuitry of a 555 timer. It actually contains 3 resistors. Usually it's in the 5 kilo ohm range. And these 3 5 kilo ohm resistors actually form a voltage divider inside the circuit. We have an NPN transistor. This is used as a discharge pin for the circuit design. Then, we also have 2 comparator circuits. These are digital circuits which has an output of high or low depending on which voltage is greater. So you'll be able to see that we have 2 comparator circuits, positive and negative inputs. If the positive input has a higher voltage compared to the one in the negative input, it would produce an output of 1. If the plus input has a lesser value than the negative or the minus input, then it would have an output of 0. Same thing goes with the comparator number 2. Okay. Flip-flop is some sort of a building block of memory circuit. So we can use this to store a single bit, either 1 or 0. So its output actually depends on the last output. Unlike with usual digital circuits without flip-flops and without memory, all outputs actually depend on present inputs or an even present output. But with flip-flops, it takes into consideration past inputs or the past output. Again, a detailed discussion of the flip-flop and other digital circuits will be reserved for the discussion of the course Digital Logic Circuit Design. Pin 5 is a control circuit. Now, the output waveform and output pin 3 has an output that goes high to low once, or can be controlled by the trigger if it's a bistable circuit, or a continuous stream of input, or a continuous stream of a square wave, high and low circuit, or high and low output. Normally, it is dependent on the connections or the design connected with pin 6, um, pin 6, pin 2, and pin 7 if I'm not mistaken. Pin 2, 6, and 7. And then those are actually controlled. Remember that we are using comparators here. So if you'll notice, in the first comparator circuit, it's connected to one of the positive inputs, which is equal to the voltage coming in or absorbed in the 5 kilo ohm resistor, which is 1/3 of the total resistance here. So imagine that this 3 resistors here actually has a voltage drop equal to the VCC supply, meaning if it's 5 volts, the totality of the voltage discharge in the resistors would be also 5 volts. But the one connected here to our first comparator circuit is only 5 kilo ohms, which is 5 kilo ohms out of the possible 15. So it only gets 1/3 of the VCC supply. So that would be around, I don't know, 1.33 volts. And in the negative circuit here, we also have connection, but this time around, it's 2/3 of the original resistance. So if there's 5 volts here, the one that would be going in as an input or going in would be around 3.67 volts, which is normally the case. Then, depending on the trigger or the input of the trigger and the dependent on the threshold, it would control the duration, the duty cycle of the output in pin 3. So 2/3, 1/3. But with the use of a control voltage, if you follow the pin 5, it's actually also directly connected to the negative part of the second comparator. We can actually use pin 5 to bypass the voltage requirement of 2/3 of the VCC supply. So if we don't want to use, let's say, 5 volts, we don't want it to be compared to 2.667, okay, or 2.67 volts. We want it to reset immediately. Okay. Then we control it, or we put a different voltage here in the control voltage. 6, or the threshold voltage, is an input we use that is actually connected externally to an RC circuit, which is the one that controls the duty cycle and duration and clock width of our output. And it is connected to the positive end or positive input of the comparator circuit, which is usually compared to 2/3 of the VCC supply, unless we connect our control voltage somewhere else. Next, discharge. This is also connected to our RC circuit, and this is used as a pathway to discharge the contents of our RC circuit. Remember that we need to have a complete circuit for the RC circuit in order to charge and discharge properly. So the contents of the capacitor circuit would actually safely discharge into the ground, as it is connected to the collector of the internal NPN transistor inside the 555 timer. And as mentioned, VCC or pin 8 is connected to our power supply. And again, what we put in the power supply actually controls the needed threshold and trigger for our two comparator circuits, which controls our flip-flop, which of course controls our pin output. As mentioned, we will be having a final discussion or a third discussion that would be focusing on some computational requirements for the design of the external circuit of the 555 timer. Of course, we cannot manipulate what's inside the 555 timer. What we can actually change is what we connect, or the values of the resistors and capacitors that we connect outside of the 555 timer. Now, let's go to the final conceptual discussion for the finals period, which is about the noise. Now, you'll have a more in-depth discussion of noise when we go into the course principles of communication, or principles of electronics communication to be exact, because some students actually mistake it as an English course, because there's also principles of communication focused on English and language, but principles of communication here refers to English communication discussion, or not electronics communication discussion. So in electronics communication, noise is termed as any random fluctuation of a signal that affects our system. So noise could come from within the system. So the components themselves in the system could contribute to noise, which is actually most of the noise that would come in or that might come in. Then we also have noise that might come in from outside the system. We call them as external noise and internal noise. The former would be the internal noise, and then the latter would be the external noise. Now, unfortunately, noise cannot be removed from a system. So any system or any signal would be affected by noise. What we could actually do is minimize the effect and minimize the noise themselves. This can be done through a number of things, which is beyond the scope of our discussion. So the types of electrical noise here shown here is just a general overview on the types of electrical noise beyond the external and internal noise. We go into specifics on the types of electrical and electronics noise. It would be more than 4. But let's have just a general overview regarding these 4 types of electrical noise. So first we have thermal noise. Thermal noise is noise caused by the fluctuations or the vibrations of molecules and electrons in a system due to heat. Remember that heat is transferred from one system to another, or heat convection happens because of the vibration of molecules. The higher the temperature is, the higher the vibration happening in the molecules. And that also affects the movement of the electrons as well. Now, the noise here is also called a white noise because the thermal noise is actually independent of frequency, meaning frequency does not affect the amount of noise coming in. So there could be a noise that could be high, low, or very high, coming from low frequency and high frequency. Next, we have shot noise. Shot noise happens from certain instances when the stream of charges actually happens in clumps or large number of individual streams instead of having a continuous charge stream. This could happen because of a number of causes, but more or less because of the clumping of the individual charge streams into large numbers, it actually has an effect on the overall output signal. Next, we have 1 over F noise. 1 over F noise is named 1 over F noise as the noise power produced by this type of noise is inversely proportional to frequency. Meaning at lower frequencies, the noise produced is quite high, but at higher frequencies, it is actually negligible. This is also termed as pink noise as opposed to white noise in thermal noise, as the frequency of pink and red, orange, yellow are actually found at the lower end of the spectrum. Now, another noise that could be attributed to 1 over F noise would be flicker noise, which happens because of the random variations in charge carrier diffusion in electronics. Remember that uh, electronics, when we talk about electronics, it has the N-type and P-type. We have the majority and minority carriers. And sometimes the majority carriers have to diffuse over to the PN junction. Okay? And sometimes because of the diffusion of those charge carriers or the lack thereof diffusion of the charge carriers, it affects the overall signal. Next, we have interference. So when we talk about interference, we are talking about usually about external sources of noise. In some texts, interference is strictly just about other signals coming in and being received by our receiver, even though it was not meant for us, or it mixes with the signal that we want. In this specific instance, in this specific text, it also includes other external sources of noise like AC signals, lightning, and such. Now, of course, if we want to determine the effect of noise in the system and in the signal, we have to be able to quantitatively measure and compare these types of noise. The three most common quantitative characteristics used to measure or determine noise are the following. So we have the signal to noise ratio, or S over N, which is technically the comparison or the ratio of the signal power over the noise power. So it's technically not the effect of noise is technically not about the noise power, but how it compares to the original signal power. So if we have a large signal power and we just have a relatively small noise power, then it would not be as big of an effect. So instead of the noise power being the sole contributor or quantitative measurement used to quantify noise effect, it's actually the signal to noise ratio. Then we want to also know the best case scenario that we have for signal to noise ratio, and that would be the maximum SNR. So that would just be the signal noise, the signal power volt or signal voltage maximum divided by the noise voltage. So this could be used either, or we could use the one that is in unitless, or we could use the one in decibels. As we have the one we discuss amplifiers, we've already discussed how to convert gain and loss in decibels. So again, if we're trying to use voltage, we use 20. If it's current, it's also 20. If it's noise, we use 10 logarithm. Another way to quantify noise would be to look at the individual noise voltage of each component. But it would be better, it would be more useful to actually quantify the individual contributions of the noise voltage within the system for each component. And that is computed as the sum of the square of the individual noise voltage, and then after getting the sum, we get its square root. So if we have, so this is example, or the formula here is for 2 specific components. If we have 3, then we extend it to plus Vn3 squared, so on and so forth. Then we add, then we get the square root. The example for computations for these 3 noise quantitative characteristics would be part of our discussion for the third part of this video lecture series. So that would also include some computations of the characteristics of the individual pins or the design for the 555 timer. Anyway, as always, thanks for listening. Have a great day and stay safe.